Today we're going to put our focus on the first of our classical methods of analysis, and we're going to talk about how we can use a precipitation reaction in conjunction with precisely known reaction stoichiometry to determine the concentration of an analyte based on the mass of a precipitate. And this method of analysis is known as gravimetric analysis. And to give you a little context for how we would use gravimetric analysis to determine analyte concentration, I want to go back to the Flint, Michigan example. We spoke on the first day of class about the role that analytical chemistry can play in protecting human health and the environment. And so the Flint, Michigan water crisis provides us a good concrete example of an analyte where we would wish to determine its concentration to immediately serve a societal good. And in the case of Flint, Michigan, the analyte in question would be lead 2 plus cation, Pb2 plus. Now, in modern analytical chemistry, we would actually quantify the lead 2 plus concentration using appropriate instrumentation, which we talked about before. Analytical chemists at Virginia Tech University determined the concentration of the lead 2 plus cation in Flint, Michigan's water using an instrumental technique called ICP. Nevertheless, we could use a classical strategy, a wet chemistry reaction strategy, to determine the concentration of the analyte if we can get it to participate in a chemical reaction which meets two criteria. First, the stoichiometry of the reaction is precisely known, and secondly, there's an obvious endpoint to the reaction so that we know when the reaction is concluded. And analytical chemistry advanced for a long time using these types of classical analysis methods. And they're still used today to validate the performance of instruments or to provide a means to check whether an interferent that's unexpected is biasing the outcome of a separate analysis that you're using. So classical techniques like gravimetric analysis, titration, and combustion analysis still have roles to play, but because they tend to be more labor intensive and depend very, very strongly on your technical expertise in the lab, they're being phased out more in everyday analysis and replaced by instrumentation. Nevertheless, we can show you how we could use gravimetric analysis to determine the concentration of lead in drinking water. So as a reminder, the EPA sets an action level for lead 2 plus in drinking water at 15 parts per billion. Now, because lead is an extremely low concentration analyte in almost all municipal drinking water, unless there's been very, very bad contamination, gravimetric analysis would not necessarily be an ideal method, particularly given the availability of instrumentation to determine the lead concentration. But many scientists throughout history have been able to use gravimetric analysis successfully to do very, very detailed and finicky chemistry and achieve some surprisingly accurate results. So the main idea in using gravimetric analysis to quantify the lead in the Flint, Michigan drinking water is we need a chemical reaction, which is a precipitation reaction, where we will have an anion or other reagent react with the lead in such a way as to form an insoluble solid which will then fall out in solution. If you're doing a gravimetric analysis for lead, sulfate anion, SO4 2-, is a precipitant, a reagent that causes precipitation, which is often used in the gravimetric analysis of lead. When lead 2 cation reacts with sulfate, it forms the insoluble solid lead 2 sulfate. Knowing the stoichiometry of the reaction between lead and sulfate is 1-to-1, we can use basic stoichiometry principles to back calculate, determine the concentration of lead 2 plus in an original drinking water sample if we know the mass of the precipitate that we collected and we know that the precipitate that we collect is highly pure. And this is the fundamental principle behind gravimetric analysis. So gravimetric analysis as an experimental technique relies on quantitative precipitation of the analyte. So what that means is better than 99.99% of your original analyte must be complexed by precipitation in order for you to determine the original concentration of the analyte based on the mass of the precipitate that it forms. If you can collect a high purity precipitate quantitatively and be sure that you haven't lost any of the precipitate, so you've obtained quantitative transfer, quantitative collection of the precipitate from the reaction mixture, you can use stoichiometry that you were introduced to early on in general chemistry to calculate the original concentration of the analyte in the sample. So to achieve this experimentally, what we would need to do is we would need to add sufficient sulfate to our sample to precipitate essentially all of the lead 2 plus as lead 2 sulfate. Now, not every precipitation reaction is suitable for gravimetric analysis. You need to have a precipitate that forms relatively large crystals that are easy to capture. It should form slowly so that the precipitate formed is of high purity. And the precipitate that it forms must be stable for the reaction to be suitable for gravimetric analysis. We'll talk about these factors in more detail in the next module when we talk about the process of gravimetric precipitation. But in general, if your reaction conditions are chosen correctly, you will lock up almost 100% of the analyte as the desired precipitate. And the desired precipitate will go slowly so that it excludes impurities from the growing crystal and you end up with a high purity crystal. As long as you collect that high purity precipitate crystal quantitatively, you will be able to use the mass of the precipitate to calculate with minimal error the concentration of the analyte in the original sample. Now, gravimetric analysis has also been historically used for quite a bit more than determining the concentration of analytes in aqueous samples. Gravimetric analysis has also been used to establish the age of minerals in the Earth's crust by quantitatively precipitating radioactive isotopes with a known half-life. And gravimetric analysis also played a huge role in establishing the atomic masses of the metals with a high degree of accuracy. So gravimetric analysis has played a huge role in the development of chemistry that we now take for granted. So the thing to keep in mind is all gravimetric analyses will follow the same basic formula. The experimental procedure, and what I mean by that is the experimental procedure may be more complex or less complex depending on what analyte you're dealing with and what chemical you add to induce the precipitation. It may be a longer, more involved experimental procedure, or it may be relatively short and only involve a few steps. But at its heart, every gravimetric analysis is based on fundamental stoichiometry, with the idea being that based on the mass of the precipitate, as long as it's high purity and you know its chemical formula, you can calculate the number of moles of the analyte that are present in that precipitate. And therefore, from the mass of the precipitate and its chemical formula, you can figure out how many moles of the analyte were in the sample originally. And then if you know with good exactness the volume of the original analyte solution, the volume of your unknown, you can take those moles of analyte divided by the volume to give you the analyte concentration. So on paper, gravimetric analysis is always an exercise in stoichiometry. In the real world, in the lab, there's a lot of deliberate experimental design that goes into designing a reliable and effective gravimetric analysis. When you guys go into the lab this term and perform your own gravimetric analysis, recognize that there's been a lot of work behind the scenes in developing a procedure that will give you a high quality, high purity, easily isolated precipitate with a stable chemical form so that you can use stoichiometry to calculate the concentration of the analyte. One other thing to keep in mind is that in gravimetric analysis, like so many classical chemical methods, you have to pay careful attention to the roles of the different chemicals. You have to recognize the speciation of the ions, and you have to keep your vocab straight. So for instance, when we talk about the product of a gravimetric analysis or the product of any precipitation reaction, like the insoluble solid lead 2 sulfate, we refer to this product, this insoluble solid, as the precipitate. But in a related word, we refer to the chemical that's added to the analyte to induce precipitation as the precipitant. Pitant. And so you have to keep your terms straight, and particularly when people are describing a gravimetric analysis, you have to listen with a keen ear to differentiate, for instance, the role of the precipitant, the chemical we add to induce precipitation, and the yield of the precipitate, the final product of the chemical reaction. And one last thing to note is that, as you guys hopefully remember from general chemistry, most precipitation reactions are actually equilibrium processes, right? And so the equilibrium concentration of the two ions after the precipitation reaction has come to equilibrium will have essentially a non-zero value. And so when you're designing a gravimetric analysis, the idea is you make the analyte the limiting reagent and you add a significant excess of the precipitant in order to force the reaction through Le Chatelier's principle to go essentially quantitatively to the product. So that's another maybe not immediately obvious aspect of the experimental design. Generally, you need an excess of the precipitant to get a quantitative yield of the precipitate. All right, so in this module, we're going to give you kind of the fundamental breakdown of gravimetric analysis in terms of how you use the data from a gravimetric analysis to calculate the concentration of the analyte, which is what we'll focus most on. But we'll also talk about how we'll also talk about the characteristics of a precipitation reaction and a physical precipitate that makes it suitable for use in a gravimetric analysis. We'll talk about the process of crystal growth, how you alter reaction conditions to get a high purity crystal, and what type of thought process has to go on behind the scenes to design an effective gravimetric analysis. And so your assigned reading for this module is going to be Harris Quantitative Chemical Analysis, just the first part of Chapter 27, sections 27.1 and 27.2, where they go over these topics. Vocabulary-wise, we're going to be reintroducing you to a number of terms that you probably heard in Gen Chem for the first time when we talk about gravimetric analysis and titration. So for today, I want you guys to start getting to grips again with, make sure you have a good working definition for gravimetric analysis, be able to differentiate precipitate from precipitant. We'll talk about the process of crystal growth, where nucleation, supersaturated, homogeneous precipitation, co-precipitation, etc. become important terms. And then on Friday, we're going to go through kind of the same treatment where we talk about a similar classical process, which is titration, and we'll go through the same kind of thought process and deal with the same kind of basic titration terms. So by the end of this week, looking forward down the road, after we cover titration or in preparation for covering titration, you should also add Harris Chapter 6, Section 6.5 through 6.7, and Chapter 7, Section 7.1 to 7.3 as part of your assigned reading. So for today, Chapter 27, Sections 27.1 and 27.2, that's all you need in terms of thinking about gravimetric analysis. But for later in the week, we start talking about titration, add these sections from Chapter 6 and Chapter 7 into the reading that you're doing. And so the very first skill we want to teach you is we're going to go over a worked example where we describe the data from a gravimetric analysis precipitation, and we'll show you how to use that data to back calculate to determine the concentration of the unknown in the original sample. And the precipitation reaction we'll be looking at is the reaction between silver and chloride to form silver chloride, where chloride will be the analyte in our hypothetical analysis. And we'll always use the same type of logic flow where from the mass of the precipitate and the known reaction stoichiometry, including the chemical formula of the product, we'll figure out how many moles of the analyte were in the original sample, then divide by the volume of the aqueous solution, which was the original sample, to get the analyte concentration. So that will be up next, and I will see you there.